Okay, we already knew that for a discrete system, for a discrete system, we have jet transform, and it is represented as that for Hn, Hl is equal to summation n equals to minus infinity to infinity Hn to the power minus n. But when we have discussed FFT for implementation of DFT, we use Fourier transform for the system evaluation. And when we have represented the transfer functions of FIR and IR, we have used jet transform. So it is quite a important thing when we discuss jet transform with discrete time signals for the implementation of FIR and IR system realization, whereas for the computer based algorithm we use FFT, implement discrete Fourier transform, and to also evaluate jet transform. Right, this is very important. We have to see the importance and the relation between jet transform and the Fourier transform. So where it comes from. So when we see this particular part, we have to involve Laplace transform in between, which is denoted by S, and S is equal to sigma plus G. Now when sigma is equal to 0, S will be equal to J omega, and this is nothing but a Fourier transform. And for Z is equal to e to the power s, that is e to the power j omega, gives the complete relation between Z transform, Laplace transform, and Fourier transform. Now this relation is very important, that is, as exponential j omega is nothing but sine omega. So we have just written from order, that is cos omega plus j sine. So mod of exponential j omega is under root cos omega square plus sine omega square, which is equal to 1, and that is mod z is equal to 1, that is equal to mod of exponential j omega. This relation holds at unit circle. Now we know for a jet transform, that is when we plot jet transform the ROC form, so we look out for the unit circle. We know this unit circle is very important, that is mod z is equal to 1, and that is also equal to exponential change. Now if you see, it is very important. At this particular point, I will just use another color. At this particular point, omega is equal to 0. And at this particular point, omega is equal to pi by 2. And at this particular point, omega is equal to pi. And at this particular point, omega is equal to 3 pi. And then again to 0 or 2 pi. Or 2 pi. Right? So it has different values of omega 0, then omega 0 dash, and omega 0 double dash, and then omega 0 triple dash. So it's a continuous increment in omega with this unit circle, right? So it is very important to understand this particular point, then we can realize the system which is represented in Z transform for the frequency domain analysis, because we are accustomed for the analysis with omega, because we represent frequency with omega or f, and the best realization we can get with omega, and we are not think about the particular point that how Z will implicate its response in terms of omega, right? So that's why I have cleared this particular point, how Z transform is related with the frequency Fourier transform, and how omega is linked with Z, right? And in terms of unit circle. Now we know the generalized difference, that is yn is equal to minus of summation k equals to 1 to m ak y and minus k plus summation k equals to 0 to n vk x of n minus k, right? Now if you take a jet transform, of the equation, that will leave, okay, yz is equal to minus summation k equals to 1 to n ak yz z to the power minus k, right? From the z transform property, k equals to 0 to n bk xz z to the power minus k, then yz plus summation k equals to 1 to n ak yz z minus k equals to xz k equals to 0 n pk z minus k. We can take yz common in this part and then put xz here. So our relation will come out to be like this: k equals to 0 to n pk z minus k over summation k equals to 1 to m 1 plus ak z minus k, right? One can see if we write this term yz over xz as h, the transfer function, that is, this is output over input, gives us the transfer function, that is hz, that is the impulse response of the system in z domain. Right, we already knew this particular part, and we can write it like this. It is h1z over h2z. Comparing these two equations, we get h1z is equal to summation of k equals to 0 to n bk segment. Now, if we take a case, for example, k is equal to 1 or k is equal to 2, for k is equal to 2, for k is equal to 2, n equals to 2, this should be n equals to 2. N equals to 2, this equation can be written as b0 z to the power minus 0 plus b1 z to the power minus 1 plus b2 z to the power minus 2. That is equal to b0 plus b1 z to the power minus 1 plus b2 z to the power minus 2. That is, it is a polynomial of order 2. So, by using basic algebra, we can find out, we know actually there will be two roots for this particular case. So, as the value of n increases, roots will also increase. Right? So we can write it like this: h1 as h1z as summation k equals to 0 to n bk z minus k in terms of root is k equals to 1 2n 1 minus zk exponential minus j omega. Now we have done two parts in this particular case. First, we have written roots as zk. Zk is called zeros, as h1z is at the numerator side, and whatever this the values of zk will give, this will make this h1z is equal to 0, and when h1z will be 0, hz will be also equal to 0. That's why it is called zeros, and we have written as zk, and we have put z is equal to exponential j omega. So we have substituted both together, so that's why our equation is like this. Then we can write it as h to z, which is equal to 1 plus summation k equals to 1 to m. And I have just to see this particular part, the limits. So h1 z is k equals to 0 to n, and this value is equal to k equals to 1 to m. Right, so we are going correct. So it is ak z minus k, and that can be written as k equals to 1 2m 1 minus pk exponential minus j omega k. Right, so we can write this particular equation in this particular format. Now, if we want to represent this hz, which is in terms of h1z and h2z, then it will have some constant b0. It is some constant, so I have written just b0. Then there will be a summation k equals to 1 to n 1 minus zk exponential minus of j omega, and then there is a thing k equals to 1 to m 1 minus pk exponential minus j omega, right? So we can take exponential minus j omega k 0 common, my exponential minus j omega k is common, then b will be equal to summation k equals to 1 to n exponential minus j omega k, and it is exponential j omega k minus zk, and summation k equals to 1 to n minus j omega k exponential j omega k minus p. Okay, this term, if we solve, it will be exponential j omega m minus n, right? So whatever the maximum values of m minus n, that will be the answer. So then there will be multiplication of k equals to 1 to n exponential j omega k minus zk, then summation k equals to 1 to m exponential j omega k minus pk. Now one can see for values of k varying from 1 to n or m, it will modify the frequency count. But the frequency will always remain from 0 to 2 pi or minus pi to pi, that is over a circle. So we will consider effect of k for further analysis. And now what analysis we are looking at? It can be seen from the representation in the z domain and its relation with exponential j omega, right? So it is imaginary of z and it is real of z, and there is a unit circle that is plotting it. Okay, so we are interested, as we know it contains different frequencies from 0 to 2 pi over this unit circle. So we are just interested at this particular frequency, and this particular frequency this particular frequency, we'll name it omega 0, and this particular point we are right now saying as point L. Right? So if we plot a vector in this direction, it has an angle omega naught. Okay, so we are interested over a system, right? And we have some system, and we want to find out its overall impact on our frequency omega naught. Let's say that particular system has, let's say that system has one pole and one 0. Pole is P1 and 0 is Z1. Okay, but so let's say pole is at this particular point. I'll just mark the pole like this. Pole is here, 0 is here. Okay, so pole is at point A and 0 is at point B. What we are interested in this particular frequency omega naught, and we want to find out the system which has this pole located at point A and this 0 which is located at point B, how they will influence this particular frequency which will come as an input, but what will be the impact when it will come out from the system. So we want to find out that particular point. If we go mathematically, so we clearly see that our transfer function Hz is defined between pole and 0, right? So this pole, the separation of this pole from this frequency and this 0 from this frequency will define how it will affect the transfer function, right, over this particular frequency. That's we want to find out. So that from this particular figure it is very reasonable, we can find out very easily if we given this point particular name with origin as C. If we give its name as C, and if we link these relations like this, right, and this one as this. Okay, now applying the vector algebra, we knew vector algebra part, and we'll just focus in that particular point, and we want to see if we can find out the impact of this pole over this L by finding out this separation AI. So if we find out by the vector algebra, so it is has CL vector is equal to AC vector plus AL vector. This is our first equation. Then also CL vector, which is this one, is equal to CB plus BL. So it is actually, it should be not AC, it should be CA, and this will be CB vector plus BL vector, and this is equation number 2. Now we knew certain parts like CL vector is exponential j omega naught, right? Because this is unit circle, that is mod z equals to 1, that is equal to exponential j omega. So at this particular point it is exponential j omega naught, and CA vector is the location of pole, that is P1, and CV vector is location of 0, that is Z1. Okay, So if we substitute this particular point and find out the value of AL and BL, then AL vector is equal to CL vector minus CA. CL vector is exponential j omega naught minus P1, and then BL vector is equal to CL vector minus CB vector, which is equal to exponential of j omega naught minus Z1, right? Now this is very important, as we have already know Hz is B naught exponential j omega n minus m, right? Okay, so actually it is m minus. K equals to 1 to n exponential j omega minus z, and k equals to 1 to m exponential j omega minus pk. So this AL gives this separation for n equals to 1. So Hz is equal to B naught, n equals to 1, n equals to 1, so it is 0, so it is B naught exponential j omega minus z1 over exponential j omega minus p1, right? So this exponential at, and for this Hz at omega is equal to omega naught, it will be B naught exponential j omega naught minus z1 over z1 over exponential j omega naught minus p. So this separation which we are discussing right now is this one. How much this pole is far from this particular point will impact its overall response, and also the how far this particular zero is from this particular frequency will impact the response of this particular system at this particular frequency. Now we want to go for a special case, so we will understand much better point. That is, if we draw again a unit circle, right? We have drawn it, so it is imaginary z and it is real z. So let's say we have a pole at this particular point and we want to find out response of our system at this particular frequency, that is omega naught. Then AL vector is equal to exponential j omega naught minus P1, where P1 is also equal to exponential j omega naught, leading to AL vector equals to 0. Then Hz at omega is equal to omega naught B naught exponential j omega naught minus z1 z1 over exponential j omega naught minus p1, where this p1 is also exponential j omega naught, leading to this particular term to 0 and this particular term to infinity, right? So what does it mean? If pole goes near to that particular frequency, the response of the system will increase towards infinity for that particular frequency. Oh, so we have come to one conclusion. Another conclusion we want to draw for the holes part. So let's say there is a hole, right, at this particular frequency, and we are saying this particular frequency is omega 1, and there is this hole, right? Now if we see for this particular point, so then dl vector will be exponential j omega n 1 minus z1, where z1 is also equal to exponential j omega. Then as z at omega is equal to omega 1 is equal to b naught exponential j omega 1 minus z1 over exponential j omega 1 minus p1. Now this z1 is equal to exponential j omega for this particular frequency, and for this particular case this will go to 0, so hz will be equal to 0. Now this is very important. You see, this is a way of discrimination against a frequency. As this particular pole lies at a unit circle for this particular frequency omega 1, this particular frequency is discriminated and it is not allowed to pass through. The response of the system is 0 for this particular frequency, whereas for the case of this particular pole and this particular frequency, the response is tending towards infinity. That means the response will be scaled much at a higher level, right? So to make and filter, the importance of pole 0 configuration is very important. When we want to improve the response of our system at a particular frequency, we will allow poles to be near towards the unit circle for that respective frequency. And when we want to discriminate against certain frequency, we will allow some zeros to be near to that particular frequencies towards unit circle, so that that particular frequency will be discriminated, right? So that is very important point that should be understood with terms of pole and 0 configuration for the implementation of filter design. Thank you. We will discuss further part in next lectures.